Photon. Yes, yeah. Yes. Just finish this one, and we're going to see what's the point. And right, okay. Oh, Mac, another account. It's nothing. This one, this one, and then YouTube, create this. All right, yeah, should be so. And we'll get to this thing. We stop this one. Let's go to this thing. Let's take a look at oh yeah. Let's take a look at this. You can see one join actually YouTube. Okay. Just have a look at and go to this and see what happened. Yeah, there are two lines. To iPhone. There's YouTube. Give a photo launch. Yes, sir. This one. Yeah. And let's connect the pipe to let's connect this one. This one is yeah, go to that and let's see what happened. Let's see SCI33206. Yes, SCI. See what's going on with this. Here. Okay. Okay. And what else? Microphone here. Okay. Okay. Good morning. Let me set the. I'm not sure when. Once we share the screen, we can use that. Usually. Why? Okay. Okay. ที่ซูมเสียงไปไหมครับที่ซูมนะครับ Let me pause the sound from Zoom is okay. Listen. Okay, the sound in test 1, 2, 3. Okay, it works perfectly. Okay, and yeah, good morning, everybody. Welcome you to SCI33206, and we are talking about the atomic model, right? We will talk about the atomic model. Let me see you here in YouTube. One share. Maybe this one. Yes. Okay, 3 people, and for the people in Zoom channel, we have five persons. I'm not sure whether there is anyone who would like to join the Zoom. No, huh? Okay, all right. So let's really start our story in the atomic model, right? We arrive at the Leadback Formula, right? Which is this one. The Leadback Formula is not difficult. I mean, I don't know what happened with your midterm exam, but anyway, I have just back from I have come back from the school yesterday evening, okay, in order to pick up your exam, okay, from your co-teachers. If you have any suggestion or complaint about the midterm exam, just let me know, okay, by typing or by any kind of communication. Okay, we arrive at. I hope that you have watched the compensation video clip that have been prepared to you during the week that I was absent due to the duty at the university. Okay, algebraic manipulation, right? It's the Leadback Formula, right? Leadback Formula is the way you could find the wavelength of the photon or the light. Okay, and it involves the initial state and the final state. Okay, you have, for example, it's derived actually from the Bohr equation, and yeah, once you substitute every constant, okay, you get RH. RH is this one, 1.09 and 737 blah blah blah. Okay, times 10 to 7, and the unit is 1 by meter. Okay, meter with the power of -1. All right. The reason why it has the unit of 1 by meter is that you can see here on the left side. Of course, you know that the wavelength is the kind of distance, right? Distance of one complete cycle of the wave, right? So the unit of the wavelength is meter, right? So the unit on the left hand side here is 1 by meter, all right? Because it's the reciprocal of the wavelength. And RH should be also 1 by meter, because here this is only the index of the orbit state of the electron in, let's say, for example, the hydrogen atom, okay, the first element in the periodic table. The final orbit state N is principal quantum number. Okay, when you go further, there are 3 more remaining quantum numbers you need to know. The first quantum number is this one, is the principal, and it's denoted by N. Okay, and the orbit state could take place in several levels. So from one level to another level, you could have different ends, and for different ends, you start from the initial state or initial orbit to another orbit, which is denoted by here as the final orbit or the final state. So you could find the emitted photon or the emitted light. Okay. Okay. The expression 31 is known as the Leadback Formula, and we're going to use it in an example. Let's say we have this one, right? At the state N equal to number 2, the second state of the hydrogen atom, find the kinetic energy, the potential energy, and the total energy, right? Yeah, of course. According to the previous lecture, we know that the hydrogen atom has the potential energy, kinetic energy, right? Kinetic energy is derived from the typical Newtonian motion, right? It's 1/2 mv squared. But because we consider the particle of electron, so this one, the kinetic energy expression should involve the mass of the electron, and we have to talk about consider the speed of the electron, and of course electron would stay at a certain orbit, right? It depends on the state, and that state is denoted by the variable n, okay, small n, and m is the mass of the electron, right, which is not so high, and the potential energy is denoted by un, which is the electrostatic potential energy. You could find from the typical Coulomb expression, right? KQQ divided by D. All right. If you go further, you will get this expression, right? And according to our previous lecture, once you substitute everything, you would arrive at the total energy as a negative 13.6 divided by n squared, right? That's the the summary of the previous lecture, right? So if you missed the lecture last time, it's no problem. But anyway, the most important expression is this one. Where could we find? Okay, this. Okay, this is the most important expression for whether a kinetic energy or potential energy. All right. This is the total energy expression. This one, right? And the potential energy is twice this one. Okay, UN is twice EN. Okay, and KN is exactly the same. No, KN is the positive version. KN is the negative version of the EN. Okay, and from this we know that EN is 13 negative 13.6 approximately. Okay, by n square. Okay, from this expression. Okay. And the unit of the energy, yeah, as I mentioned last time, it's no longer in joule anymore, because we are in a tiny scale, tiny object. So the most appropriate unit is going to be electron volts, as you have seen here. Okay, all right. So in order to deliver the answer to this first sub question, kinetic energy, right? So let's add it. Kinetic energy, Kn, will be the negative version of En, right? So negative of minus 13, it will be the kinetic first, right? The kinetic energy is going to be the positive of this value. Okay, is negative of what? Negative of minus 13.6 divided by n squared. All right, so we will end up with the positive value of that n squared. And of course, the electron stay at the second orbit, which is denoted by n equal to 2. So we're gonna see, we're gonna derive K2, right, which is 13.6 divided by 2 squared. All right. So once we use the calculator, where is that? Okay, it's 13.6 divided by 4, right? It's 3.4. So this one is 3.4, and of course you know that the unit of the energy right now is in electron volt. If you wanna convert it to joule, you have to multiply this value by the electron charge, but the unit is in joule. Okay. Yeah, that's K2, and we have already provided the answer here with kinetic energy. The next one มีใครจะเข้าที่ซูมไหมครับผมจะดูเรื่อยๆนะเดี๋ยวค้างขึ้นมานะครับถ้าเข้าก็sorry เข้าได้เลยนะครับผมไม่เห็นนะครับขออภัยด้วยโอเคเดี๋ยวผมเปิดไลน์ดูด้วยแล้วกันนะครับคุณพิมพ์อะไรมาครับ Where is that okay no one okay yes the next one is the potential energy, right? It's UN, right? UN is twice, right? Twice the total energy, so it's 2n minus 13.6 6 divided by n square, right? So you could see here 2 minus 2, right? In 13.6 divided by n square, right? So for U2, when n is, oh no, when n is number 2, you're gonna get minus 2 and 13.6 divided by 4, right? So it's twice of this value. It's 2 times this value. So it's 6.8, right? But it's negative 6.8 EV. Okay. Please note that the kinetic energy is always positive, but the potential energy could be negative because it is something about a negative charge, right? The electron is negative charge, so it could be negative. All right. Yes. The last one is En, right? En is, of course, we know it's 13.6 divided by n square, and for E2 we would get 13.6 divided by 2 square, and that's the negative value of 3 point. For the unit is electron volts. All right, here we have deliver 3 answer already. All right, yeah. That's the first question, right? The kinetic energy, the potential energy, the total energy. Let's check whether it's correct or not. Okay, it's already 5 minus negative 3.4 EV, negative 6.8 for the potential energy, and the kinetic 3.4 EV. All right. And the next one is find the wavelength of the photon emitted from the electron transition to state n equal to number 2. All right. So according to this one, in from 1 to 2, right? So initial state, yeah, we have to write down here Ni is number 2, Nf is number 1, right? Why? Because they say that first electron, which is denoted by this particle, the electron stay at the second orbit or state number 2 in electron moves to the first state. Okay, they move to this location, to this orbit, and of course the Bohr or the Leadback formula will be valid when Ni is greater than Nf. Okay, and once it moves to the lower orbit, the electron will emit the photon. Okay, and here is called photon, which is a packet of energy or the light. Okay, what we could observe is the light. All right, and that's the reason why we could see the discrete spectrum. It's not continuous spectrum. Okay, that's the whole behavior or whole mechanism in the second sub question. And the formula we're going to use is this one, the Leadback formula, right? So let's consider the Leadback formula. It's 1 by lambda n h 1 by nf square minus 1 by ni square. All right. And as you know, you have to be sure about Ni and Nf, right? Ni is number 2 and Nf is number 1, right? Right here. And yeah, we go further on the next page. Yeah, Ni is number 2 and Nf, the final state, is number 1, right? From the second orbit to the first orbit. Yes, of course, we write down the left-hand side, and IH is 1.0897 times 10 to 7, and 1 by NF. NF is number 1, right? So it's 1 square minus 1 by 2 square. All right. And yeah, we're going to see it's lambda is going to be the leadback. Leadback. You could see that this is the 4, right? 4 times number 1 is going to be 4, and 4 minus 1 is going to be 3. So you have 4 by 3 and 1.097 times 7 here. All right, and you leave it into the calculator. You're going to get the wavelength, right? So RH, Leadback Constant, is 1.097373738.527, and E7, right? That's the Leadback constant, and you see it's lambda, right? Lambda is 4 by 3 times Leadback constant. It's 1.215 times 10 to 7 meter, or let's check whether it's correct or not. Okay, yeah, it's all right. And if you convert it to the nanometer, right? More visible light is represented on the scale of nanometer. So yes, of course, it's going to be 1 to 1.5, okay, nanometer. All right, and that's it for this problem. All right. For the problem about the kinetic energy, potential energy, and total energy. All right. And finally, they want to know the Leadback, the wavelength, right? The wavelength of the photon or the emitted light, and we have applied the Leadback formula, right? Now let's move to the next page, of course. And as you know, the Bose atomic model could give you several possible transition of energy from any orbit, right, to another orbit. But under the condition that the initial state should be greater than the final state, right? Ni should be greater than Nf, right? But not only Leadback, but also many people many physicists have discovered the transition of the electron from one orbit to another orbit, for example, but it's not observable by eye. Okay, the visible photon is given by the Leadback, but there are also other transition regions. For example, the transition from whatever electron orbit to the first orbit, which is 13.606, to this orbit, for example, to the second orbit, from the second orbit, from the third orbit, 4 to 5, okay, to the first orbit is called Lyman series, okay, and from wherever the electron moves to the second orbit, it's going to be called Balmer series, and from whatever electron orbits, okay, the final electron orbit as number 3 is going to be called Photon series, okay, but some of these may not be completely observed by human eyes. Okay, this is taken from the book number 1. This is the book number 2. You could see it's not exactly 13.6, it's 13.606 if you go into more digits, right? I'm gonna watch whether anyone who would like to join the Zoom meeting. All right. Anyway, the Bohr models is the general one, okay, that can describe any series. Okay. There are many physicists or scientists who observe the transition of the electron from one orbit to another orbit, but it depends on your apparatus, okay, your measurement device, whether it could observe the photon in that spectrum or not, in that frequency or not. Okay, of course, if you use your eye, you could see only the visible range of the light, but there are also other possible electromagnetic wave radiation. For example, Photon series. Okay, Photon series is the number 5. Okay, the electron orbit number 5 from wherever. Okay, but the initial orbit should be greater than number 5. Okay, and the bracket series. Okay, bracket is another physicist who observe also this light transition. All right, and yeah, if this is what we draw in a straight line, right? If we draw in a circular way, we would have that's the number 1, right? It's Lyman series, it's ultraviolet region, and the Balmer series is the visible light. Okay, this is the region that human eyes could observe, and Photon series is beyond our eye, infrared. Bracket series is also infrared. Photon series is infrared light. Okay, that should be measured by spatial device. All right, Photon series is the Photon series has the destination of n equal number 5 and equal to number 5, and the bracket series is has the destination as n number 4. Photon series has the destination as n number 3, and so on. Okay. Okay, let's consider the Balmer series. Balmer series has the destination orbit as number 2, right? N equal to 2. From wherever n, okay, which is greater than number 2. The Balmer theory of the hydrogen atom corresponds to the state with quantum number. This is the principal quantum number n equal to, as in figure 21 to 23. Okay, this is taken from book number 1 in straight line manner. This is taken from the book number 2 in straight line manner, and this one is taken from book number 2 too, but it's in the circular way. Okay, it's the same thing, but you just draw it in a circular way. This is the correct one. Okay, actually, of course, atom has the shape like a sphere, right? Spherical shape. Okay, let's pay attention to the Balmer theory. Balmer theory has a destination of n equal to number 2, right? In Balmer series, okay, let's pay attention to this. In Balmer series, find the longest wavelength of the emitted photon and its frequency and energy. Find the shortest wavelength of the emitted photon. So they ask us 2 quantities, okay, which is similar and which are also quite different from each other. Okay, the Balmer theory has something to do with n equal to number 2, right? That's the second orbit in and of course the initial state should be greater than number 2. Okay, Ni should be greater than Nf, and Ni could start from wherever, okay, from whatever n which is greater than n equal to number 2. All right, and if you get into the detail, n equal to number 2 has the energy as negative 3.4. Why negative 3.4? This is the value we have got before, right? Negative 3.4. That's the total energy En we have got from the previous example, from state number 2 to state number 1, right? And that's the same thing. State number 2 has the energy as 3.4, right here. And if you get into the detail of state number 3, number 4, 5, and 6, you could get the numeric value here. Okay, let's talk about our destination. They want to find longest wavelength and the shortest wavelength. How could we solve this? Which wavelength could give you the highest amount of energy? Which one? Should the longest wavelength will provide you the maximum energy, or the shortest wavelength will do? And of course, you know that E is equal to HF, right? And if you draw it again, F, C is lambda F, right? So if you express it in terms of lambda, you're going to see HC by lambda. All right. Okay. HF Emax will happen from the lambda mean, right? The minimum value of lambda will give you the maximum energy, okay? And the minimum energy will happen due to the wavelength that is maximum. All right, because if this one is maximum, it stays at the denominator. If the denominator is large, this one is going to be small. But if this one, the wavelength is small, the energy is going to be large, which is the case here. And they want to find the longest wavelength. Longest wavelength means the lambda max, right? And it's going to be minimum energy right here, right? So let's take a look at the diagram. Which one is the minimum energy transition? Which one? This one or this one? You could see that the maximum energy transition is the one that starts from n equal to infinity, this the ni, right? And nf equal to number 2. And here will be the E max, okay, the maximum value of the energy. But this one is in the Balmer series, okay, in Balmer series. Let's restrict ourselves to only Balmer series. That's the Balmer series, okay, the maximum energy is given by the case from Ni equal to infinity to Nf as number 2. And for the minimum energy, case, we have the final orbit as number 2, and the minimum one should be Ni as number 3, okay, because this is the least possible, right? Here you're gonna have E min. มีใครงงตรงนี้ไหมครับมีใครงงไหมผมสวิตช์มาภาษาไทยนิดนึงครับพลังงานสูงสุดเกิดได้เมื่อคุณกระโดดจากที่ไกลที่สุดใช่ไหมเพราะนี้มันเป็นความแตกต่างของพลังงานใช่ไหมครับ E max เกิดขึ้นได้เมื่อ n คุณเยอะที่สุดนั่นคือ infinity นะคุณไม่เกิน infinity แน่นอนครับดังนั้น E max จึงเกิดจาก n เท่ากับ infinity มาสู่ n เท่ากับ number 2 number n หมายเลข 2 ครับ n เท่ากับ 1ไม่ได้นะครับเพราะว่าเราพูดกันเรื่อง Balmer series นะเราไม่ได้พูดเรื่องไลมันนะครับเห็นไหมไม่ใช่ไลแมนนะไลมันซีรีส์นะครับไลแมนก็ได้แล้วก็ E min นะครับพลังงานน้อยที่สุดก็เกิดจากการกระโดดจากสเตจ3มาที่สเตจที่2นะครับออร์บิทที่3มาที่ออร์บิทที่2นะเพราะว่ามันเป็นเวกเตอร์ที่น้อยที่สุดแล้วนะครับการลูกศรที่สั้นที่สุดแล้วเนาะ 2.5 ก็ไม่มีเนาะเขาเป็นเลขอินทิเจอร์เสมอเลขจำนวนนับเสมอครับ so E min will take place from n equal number 3 to n equal to number 2. All right, and what is that? So let's find the longest wavelength. The longest wavelength will correspond to E min, right? Longest wavelength is over here. Longest wavelength will be here. And here you would have shortest wavelength. Shortest wavelength. All right. So let's get into the detail of where is that? the expression we could find, right? We could use I think the Bohr series, right? This Bohr series, this one, equation number 30. Okay, we could not use, we could still use the Leadback formula, okay, because Leadback formula is valid for any state, right? We are going to use I think we could use yes, we could use the Leadback formula in the Leadback formula for the shortest wavelength. We have initial state as infinity to NF, right? So let's substitute it.นะครับไม่มันดังครับลดเสียงนิดนึงครับผมมีตัวมอนิเตอร์ครับโอเค1 by lambda is equal to RH, right? The Leadback constant, and 1 by NF. You know, NF is number 2 square, right? And minus 1 by infinity square, right? And you know, infinity square is 0, right? So is right here you would get you would get lambda min. Okay, 1 by lambda min is equal to RH. Okay, and it's here is 1 by 4, right? So lambda min is 4 by RH. Okay, 4 by RH, and if you substitute the value of RH, you would get I just 4 by 1.097. Oh. 1.097 times 10 to negative 7, right? And it's gonna be yeah, 4 by RH is 3. Okay, it's 3.6451 times 10 to negative 7 meter. And if you want to express it in terms of nanometer, right, it's going to be 364.51 in nanometer. Okay, and that's the shortest wavelength you could get from the Bauer series. And let's move to the second case. The longest wavelength will take place from the minimum energy, right? So the minimum energy will be the case once you 1 by lambda max is, this is the Leadback formula, right? RH and 1 by Ni. Ni, the initial stage is, you can see here, we start from number 3 to number 2, right? So it's 1 by 3 square. 3 square minus 1 by 2 square. All right. And yeah, you could see that it's, is that correct? Initial state is number 3. Oh, sorry for that. If first initial, no, it's initial first, so it's number 2. And the final state comes later. It's number 2 and 3 square, right? So you could see that this is number 9. Here is the number 4, right? So you could get lambda max. Lambda max will be 9 and 4 and RH, and of course 9 minus 4, right? It's, yeah, you could put it into the calculator and you get the longest wavelength, right? 4 and 9 times 4 in RH times 9 minus 4, and yeah, you would get อันนี้ผมกดเครื่องคิดเลขข้างนอกนะครับไม่ได้ครับนี่เพราะว่าสลับจอไปสลับมาเดี๋ยวมีทำให้คุณเวียนหัวนะครับ it's 6.56 and 1 times 10 to negative 7, and it's in meter. And if you want to convert it to nanometer, right, nanometer is going to be 656.11, and here is in nanometer, right? Yeah, you get the longest wavelength, and if you don't believe me, you can compare it, right? It's 364 nanometer and 656 nanometer. This one is greater than this one, right? So it's lambda max, the longest wavelength, and the shortest wavelength, lambda min, is only 300 nanometer, right? It's I hope it's fine. It's already correct, right? Okay. The solution provided here involves the mathematical derivation in optimization, which is a higher level. But if you take a look by eyes, you just simply see that the shortest arrow will take place from number 3 to number 2, and the longest wavelength will take place once you start from n equal to infinity to n equal to number 2, right? The longest arrow here. Okay, let's check the lambda mean. Lambda mean, where is that? Lambda max is 656. It's all right. Lambda mean is 364. Yeah, which is correct here. Okay, now let's go ahead with the next sub question. Find the longest emitted photon and its the frequency and energy too, right? The shortest, right? Shortest one. Okay, this is the shortest wavelength you could get, and the shortest wavelength will correspond to the maximum frequency, right? Because f c is lambda, f is z by lambda, right? So f max will be z by lambda mean, right? And yeah, let's say for simplicity, c equal to 3 times 10 to number 8 meter per second, and lambda mean is 364.51 nanometer. So f will be that. Okay. This is the lambda mean, and we're gonna divide 3e8 divide this one. We're gonna get the frequency of 8.2303 times 10 to 14. Okay, that's in hertz. Okay, cycle per second. That's the maximum frequency, and the next one is the maximum the maximum energy, right? Maximum Emax. Emax will be E equal to HF, right? And if you wanna express it in terms of EV, you don't have to use the Planck formula, Einstein-Planck relation. You just use the Balmer formula here. Okay, where is the Balmer formula? Balmer formula is right there. It's here. Okay, I don't know. You just use the Balmer formula. No, it's En. Okay. Emax is not this one. Okay, Emax is the energy from n equal to 2, right? Because we are talking about the Balmer theory at the second. So E2 minus E infinity. So this one is minus 13.6 divided by 2 square minus, minus 13.6 divided by infinity square, right? Infinity square. Of course, even only single infinity, this term is gonna remain 0, and is that all right? Balmer is in corresponding to number 2. So if you divide 13.6 by number 4, it's gonna be I think it's 3.4 again, right? Yeah, it's minus 3.4, but the unit here is EV. Okay, if you want to have it into scale, in the SI scale, you have to multiply by the electron size 1.6 times 10 to negative 19. All right. Yeah. Let's check whether our answer is correct or not. E max or E min? E max, right? But why I calculate E min? ทำไมผมใช้ E min แล้วนี่ they asked us about the longest wavelength emitted and its frequency. Longest wavelength. Yeah. Oh, longest wavelength. So it's incorrect. ผมพาหาผิดนะครับ เราต้องใช้ lambda max นะเพราะว่าตามโจทย์บอก longest wavelength. So we have to use the lambda max. I'm sorry for that. Anyway, you can see the Emax, right? The maximum energy. And let's see the F min, okay? F min could be found from C by lambda max. Okay, C by lambda max, C is 3 times 10 to 8. And lambda max is this one, is 6.5611 times 10 to negative 7. And you're gonna get that. All right, so 3 by 8. And what is that? No, 3 by 8. Okay, here. 3E8 divided by this term, and it's gonna correspond to the minimum frequency. It's 4.572 times 10 to 14. The unit of the frequency is hertz, right? And yeah, and now let's consider the minimum energy. E min. E min will be C by lambda min. Okay, C by lambda. Oh, sorry, E min C by lambda max. Lambda max. So it's oh no. This is E min. I'm sorry for that. E min will be and you know that E min is the energy where electrons start from n equal to 3 to n equal to 2, right? So it's initial to it's I don't know, it's EF minus EI. I hope it's EF minus EI, right? Let's check again. EI minus EF, okay. EI minus EF, E initial from E3 minus E2, right? So E3 is minus 13.6 divided by 3 square minus 13.6 divided by 2 square. All right, and you're gonna get, I'm sorry for that, minus 13.6, 1 by 3 square minus 1 by 2 square. All right, and yeah, if you get into the detail, you could find negative 13.6 and 4 minus 9 divided by 9 in 4, right? And if you put it the negative to that, you're gonna get 13.6 and times 5 by 36, right? Let's see what is that then 13.6 times 5 by 36 is 1,999,881. 1.889 EV. Okay, 1.889 EV. I'm not sure whether it's correct or not. It's quality, right? E-min, right? E-min. E-min is this one. Okay, all right, it's correct. I think one here you could see the result. Okay, 1889. Okay, 1889 EV. All right. You go further in more precise digits. You can do it. Okay, and yeah. Let's move to the next story. We still have 15 minutes, right? Kanok. Oh, it's something else, right? เดี๋ยวจัดการครับปัญหานั้น what's going on in the SKE โอเคเขาแจ้งเรื่องการส่งคะแนนเก็บคุณนะครับใครไม่ได้ส่งกันบ้านคุณนั่นนะส่งย้อนหลังก็จะนั่นแหละครับ 0.75 นะผิด 0.5 นะครับ Okay, all right. Now we move to the next story about Bohr model. Okay, so what is going on with Bohr model? Bohr small atomic model tell you about the electron orbit, right? From infinity orbit to n equal to number 1, number 2, number 3, and blah, blah, blah. And there are several scientists or physicists, okay, like Baumer, Lyman, Photon, okay, and so on, who discovered spectrum of the light, okay, whether in the visible lens by human eyes observation or out of the human eyes scope, okay, like in ultraviolet or infrared and so on, right? Apart from the wavelength or the frequency of the light, Bohr model also talks about the radius of electron. Okay, the radius is not the precise radius, but it's somehow like the mean value of the radius of the electron that of the atom that electron is moving around. Okay, and yes, now let's talk about it. The radius of an atom could be found from in quantum state. Okay, which orbit you are going to observe. Okay, if you observe the larger orbit, the radius of atom is going to be large. Okay, if you consider the fundamental or the basic state like n equal to number 1, that's the smallest size of the atom. Okay, so radius depends on the in quantum number or the in quantum state. The Bohr's model provides the atomic radius too, right? It's okay. We start from the simplest atomic model, okay, which belongs to hydrogen atom, okay, that has only a single electron and a single proton. But Bohr's model could also describe or explain some behavior of the bigger atom like helium, neon too. But we will see that later. Okay, we start first from the more simple case. Okay, the simplest case like hydrogen atom, which has only a single electron. Okay, the radius of the electron of the atom from the n orbit is given by this expression. It's n squared and h flat. Okay, h flat is the circular version of the Planck constant, and me the mass of the electron, and ke is the Coulomb constant, and e squared is the charge of the electron. All right. And epsilon 0 is the electron permittivity, right? If you express it in the H-land, you get this term. If you express it in a typical way, in the max conventional max constant, you get this one. And once you substitute everything, every constant here, you would get this result, which is simpler for you in the high school level. Okay, it's 0.05 m squared. All right, and the unit for this is unfortunately not in the SI standard scale. Okay, it's in the nanometer. Okay, nanometer is the basic unit for the distance about the light, for the wavelength of the light that could be observed by human eyes. Okay, and atomic mass unit U. Okay, here we arrive at a spatial unit, which is called atomic mass unit. It is defined as 1/12. Okay, 1/12 of the mass of the carbon 12 atom. Okay, you know that the A atom could have I don't know what to say. It's like a relative, okay, a brother or sister, okay. But the brother and sister of the atom is not like what we call in family, right? It's known as isotope, right? Carbon has also some other isotope like carbon 13, carbon 14, but carbon 12 is the basic one, and that's the standard. Okay? I'm not the person who set up this standard, but it's from the chemists and physicists. Okay, they say the atomic mass unit is 1/12 of the mass of the standard carbon, which is carbon 12 atom, and that's basic isotope of the carbon. Okay, you could have also carbon 13, carbon 14, which might not be so stable. Okay, you will see the half-life later I think in the next chapter. That's the nuclear physics. Okay, yeah. At least on this page, you get to know the radius of the atom, which is described by this expression 0.5. That's only the approximation. 0.05 m squared. Okay, the unit is spatial, which is in nanometer. All right. Now let's take a look at summary of fundamental subatom particles. Okay. Now you see the bigger view, bigger image of the atom, right? Characteristic neutron. Of course, we have three main subatomic particles at the high school level, but if you go further in bachelor degree or master degree or in doctoral degree there, or even here in this in high school level, we will see some other tiny particles which is smaller than neutron, proton, and electron. Okay, electron is only the tiniest elements, but not this one, neutron and proton. Okay, let's let's summarize some behavior of the atomic particles. We have symbol, location, mass in the SI scale in kilogram, mass with respect to the electron, which is called electron relative mass, and the mass in here the atomic mass units. We have the mass in Einstein scale. We can make electron volt per c square. Okay, that's derived from the Einstein relativity expression, right? EmC square. Okay, if we express it, you know that there is a E equal to mc square. That's the transition between the mass and the energy, right? That's used in nuclear bomb development, right? But I would not recommend you to do that. Okay. Anyway, it's derived from this expression. A charge of these three particles, a spin value of these three particles. Okay, spin is the next property of the of any particle, okay, not only electron, a neutron has also spin behavior, proton has also a spin behavior. Every subatomic particle has its own spin, okay, spin behaviors. Spin is known as, if I can remember, is the third or fourth quantum number, okay. Okay, let's consider first the neutron. Neutron could be written whether in physics or in chemistry, like n with the power of 0, or n with, this is in atomic expression, 1 proton and 0 neutron, right? And for proton, you could say it's P plus, okay? 0 here means it has no charge at all. And plus, as the power here, it means that this particle has the charge in the sense of positiveness, okay? And in atomic expression, it has 1 proton and one atomic number. Okay, the summation of neutron and proton here. And electron could be written as E with the power of the negative side. The negative side stands for the negative charge of the electron. Or in terms of atomic expression, electron has no proton, so that's why we have 0 here on the left-hand side, okay, and the power left. And on the subscript, in the left side, we have -1 because we don't have proton at all here. We don't have proton. Neutron has no proton, so that's why it's 0. But electron has something in the opposite way. It's not proton. It's the charge which is reversed to in a converse way to proton. So that's why they say -1. Okay, and location, and of course, neutron is gonna stay at the nucleus of the atom. A proton will stay at the nucleus of the atom too, right? And electron will not stay in the nucleus at all. Electron will stay at the orbit. Okay, that's the effort by physicists who try to explain everything, who would like to know something about the atom, right? They found that the electron is moving around the nucleus, and you have seen already there are several orbits, whether it's Lyman series, Bauer series, Fun series, and so on. Okay, the mass of these 3 subatomic particles in 10 to the -27 kilogram. This is in the SI scale. Neutron and proton are in the same level. It's 1.67. Okay, the first 2 digits after the decimal points are quite the same. Okay, are quite the same. But the digits after that, in the 3rd or 4th location, proton and neutron are quite different. Okay, and yeah. Anyway, neutron and proton are on the same scale, 10 to the -27, and electron is lighter than these 2 particles. It's in -31 kilogram. It's, as you know, it's 9.1 10 to -31 kilogram, right? That's the mass of electron in SI scale. But if you work in sub areas in physics, they would not consider the SI scale because it's not convenient for them. Sometimes they want to see the mass of that particle with respect to electron. For example, the mass of neutron compared to electron is going to be 1,942. Okay, and a proton has a mass of 1,036. Okay, neutron is a little bit heavier than the proton. Okay, this is heavier than electron. Electron is number 1 because it's mass of electron divided by mass electron, right? For the mass in atomic units, neutron has the mass like 1.0 blah blah blah. Okay, it's not the absolutely one. Okay, proton is not exactly number one. It's 1.0 blah blah blah, and electron is even tinier. Okay, it's not one at all. It's less than one atomic mass unit. You can see here 1, 2, 3, 4. Okay, 4 point after the decimal unit. Okay, and if you want to see what is one atomic mass unit, one atomic mass unit is 1.66 10 to negative 27. Okay, which is in the same scale as the mass of neutron and proton. All right. For the mass in terms of Einstein equation, mass to energy, the neutron has the mass as 939. Proton has the mass, in terms of mega electron volt per c squared, 938, and electron has the mass of 0.511. Okay, and 1 mega electron volt is 1.6 blah 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 10 to 13 joule. A charge of the electron could be found from this. Okay, 2.3, 2 by 3 times plus 2 and divided by times negative 1 by 3 is going to remain 0. It has no charge at all. And for proton, you just multiply this value. This is the mass of, this is the charge of the tinier particle. You will see it later. This one, it's called up quark and down quark. Okay, proton has 2 up quark and 1 down quark. Neutron has 2 down quarks and 1 up quark. Okay, and that's why the way to calculate the charge would follow from that composition. And the neutron has two down quark, right? So 1 down quark has negative 1 by 3 charge of the electron, right? So 2 times negative 1 by 3. And the 1 up quark is 1 up quark corresponds to 2 by 3 charge. So the summation of this one is going to be 0. And for proton has 2 up quarks, so 2 times 2 by 3. Okay, that's the 2 by 3 is the charge of the up quark. Long. Oh no. Later. Beended.
All right. Yeah. That is. Okay, ใช้สีแดงอยู่นะครับ Okay, now let's continue our lecture. Okay, we will finish soon once we finish this table. Okay, the charge of the proton is number 1. It's a positive one, right? Electron has negative 1. And for the spin number of neutron is 1 by 2. Okay, the same thing. A proton has spin number as 1 by 2. 2 an electron has spin number 1/2. The unit of spin is h slash. Okay, h slash is, as you know earlier, the h slash is the typical max Planck constant divided by 2 pi, right? It's 1.05 times 10 to the negative 34 Joule second. Okay, and that's it for the today's lecture. Okay, see you วันนี้ก็คงจะจบเลคเชอร์ไว้เพียงเท่านี้นะครับใครไม่ได้พิมพ์ชื่อก็พิมพ์ชื่อมานะครับการบ้านเหรอการบ้านนะครับสำหรับ604นะครับการบ้านก็ให้ทำเรื่องเนี่ยครับก็คือเรื่องBohr model นะครับ Bohr model the homework is something about Bohr model like the problem of energy transition or the radius, okay, or the potential energy, kinetic energy, or total energy in this story, in this topic, okay, or even you could find the energy of the photon, okay, and we will talk about it later. Okay, so today's lecture is gonna finish. See you on, I don't know, maybe we would have the compensation of the missing lecture. I don't know. I'm talking with your teacher in I don't know, in the subject that they have done last week. Okay, นะครับก็จะไม่แน่สัปดาห์หน้าจะมีชดเชยนะครับวิชาสังคมหรืออะไรที่คุณเรียนไปนะครับก็ผมก็จะอาจเข้าไปแทนกำลังติดต่ออาจารย์หรือคุณครูคนนั้นอยู่นะครับโอเคการบ้านนะครับก็คือทำเรื่องที่เรียนไปนะครับได้แก่โจทย์พวกเรื่องenergy photon นะครับพลังงานของโฟตอนหรือว่าการเคลื่อนย้ายจากสเตจหนึ่งไปสเตจหนึ่งหรือว่าจะหา radius ยังไม่ทำเนาะก็ radius ไม่ต้องนะครับโอเคสวัสดีครับบ๊ายบายครับสำหรับ M604 นะครับBegin turn on. this. Oh.ครับพี่วันสวัสดีครับครับพี่วันสวัสดีครับกำลังไปเปิดดูครับขออภัยด้วยครับพี่วันตะกี้ผมติดธุระเลยไม่ได้รับสายโอ้ผมยังไม่ได้ส่งรายชื่อให้นี่คือตรงตามในสุพีมเลยใช่ป่ะหรือว่าได้ชื่อมาครบอยู่แล้วที่นิสิตได้อันนี้เรียงตามตัวอักษรหรือเรียงตามรหัสโอเคไม่มีปัญหาผมก็ลืมส่งไอ้นั่นให้เลยลงชื่อจาก SW ให้ชื่อจากสุภูมิโอเคครับได้โอเคครับขอบคุณมากกำลังครับ Which has the Photon as the first person. 3, 4, I'm not sure. Okay, that's the M604. Petra as the first person. Where is the Petra? The second person. Class such a school. Oh, 10 already. Okay. Okay. That's now we arrive at the section of M605, right? The section of M605. That yes, patterning. Okay. I need to open the file again for M605. Close this into model. Oh no, undo. Oh no. No. Atomic physics 20. Oh no. No. Oh no. Again. Physics. So that. This 9. Yes. 9. Get to watching now. And we would say this is the physics, and this is the section of M605. Today is 24. 2021. Yeah. And YouTube. 5. First and 6. Atomic physics. Let's see this one. Okay. Yeah. Let's go to 605. The Leadback Formula. Okay. Good morning, everyone. Welcome you to SCI33206, and this is the physics number number 5, right? If you have any problem about the midterm exam, just let me know. Okay. Otherwise, we're gonna go further. ถ้ามีปัญหาเกี่ยวกับถ้ามีปัญหานะครับเกี่ยวกับโอเคมีปัญหาเกี่ยวกับตัวข้อสอบนะครับก็โปรดแจ้งผมได้นะครับโอเคไหมก็ผมก็อยากรู้ว่ามีอะไรที่คุณไม่สะดวกไหมอะไรอย่างเงี้ยครับก็คือยากไปไหมหรือว่าเวลาไม่ทันเวลาไม่พออะไรนะครับพิมพ์มาได้นะครับพิมพ์แจ้งที่ทางไหนก็ได้นะครับโอเคไหมคนอยู่ที่ซูมก็พิมพ์ชื่อที่ซูมมาครับOkay, we arrive at the Leadback Formula, right? On this one. Leadback Formula. We have already calculated that the work function. Leadback Formula. Somehow, yeah, okay. Yeah, Leadback Formula. Okay, ก็มีคนพิมพ์ชื่อมาแบบที่ YouTube ทั้งสองนะไม่ทราบว่าซูมมีใครจะเข้าอยู่ไม่มีนะมีธนกรคนเดียวนะครับมีที่พิมพ์ชื่อมาก็คือธนกรคนเดียวนี่นะครับokay, let's capture who else นนทกรนะครับyeah there in the YouTube channel Streamlabs to YouTube iPhone, right? And Zoom to YouTube, we have Kitapop, Panatat, Sit, Supavit, Pravat, Tutinan, Thanathon, Natawin. And in Streamlabs to YouTube, we have Nathon, we have Piratat, we have Warinton,วชิรวิทย์นนทกร alright ครับก็ถ้ามีปัญหานะครับเกี่ยวกับข้อสอบที่ผ่านมานะว่าทำได้หรือไม่ได้ยังไงครับก็ให้แจ้งผมได้นะโอเคไหมจะได้ปรับต่อไปนะครับให้รุ่นน้องคุณได้เรียกว่าอะไรดีกว่าเดิมนะครับโอเคไหมผมก็ไม่รู้ว่าผมจัดยากไปหรือเปล่าอะไรอย่างนี้นะครับAll right. If not, then let's continue our story in Leadback Formula. พิมพ์บอกได้นะครับส่วนใหญ่ทำกันทันหรือเปล่าครับมันไม่ได้เข้ามาที่ซูมนะผมก็ไม่รู้ว่าคุณทำกันได้หรือไม่นะครับโอ้ผมใช้ไมโครโฟนผิดหูฟังผิด All right. Yes. So now let's continue our story in the Leadback Formula. I hope that everyone in M605 have visited or he have seen the compensated lecture, right? I hope that you have spent some time in order to watch the compensated lecture so that you can keep up with the current situation of the lecture. Okay, ใช้ได้นะครับกล้องอะไรใช้ได้นะผมเซตให้นะครับ Okay, the Leadback formula is in equation 31. Okay, number 31, and it's the expression about the wavelength, okay, of the emitted photon or the light. Okay, simply speaking, it's the wavelength of the light. All right, it has something to do with the constant, and this constant is developed by Leadback. That's why scientists have to give the dedication to him. It's called Leadback Constant, and the whole expression is called Leadback Formula. Okay, Leadback is Swedish. I think he's a physicist, Swedish. He has discovered this work. Okay, he's developed this expression from the Bohr, okay, from Niels Bohr. And if you have ever read the Life by Leadback, you would be amazed with his life. Okay, he is a professor working at the university, but at the same time he also worked as consultant, okay, in the bank. Okay, all right, it's quite surprising, right? Yeah, anyway, one of the most notable contribution from him is the Leadback formula, okay, which is actually developed from the Bohr's Niels Bohr formula. All right. Yeah. Yes. The Leadback formula has two more variables. That's NF and another one is NI. Okay. NI is the initial state or initial orbit of the electron. Okay, and to the final state, to the destination. For example, you have here NF, that's the final state, which should lie lower than the initial state. Okay, NI is over there. Okay, and electron is moving to this state, and it's gonna emit the light. Okay, this is the photon, emitted photon or emitted light. Okay, photon is a packet of the energy. All right, and that's the basic thing you need to know. In lambda here is the wavelength of the photon or the wavelength of the light, whether it could be observed by human eyes or not. Okay, for example, the infrared, ultraviolet is the region which could not be observed by human eyes, right? Okay, yes, Leadback constant is, after you substitute everything, right, in the Bohr's formula, you will get the Leadback constant, which is 1.09 times 10⁷ 1 by meter. Okay, and in front of this, in the unit of the Leadback constant is 1 by meter, and you may ask me why we have the Leadback constant as 1 by meter. Because on the left-hand side here in equation number 31, you can see that the Leadback, the unit of 1 by lambda is 1 by meter, right? Left-hand side here is 1 by meter because lambda has unit of meter, And on the right side, you should have also the same unit, right, which is 1 bar meter. So Leadback constant has unit of 1 bar meter or meter. Meter leads to -1, right? And in the parentheses, there is no unit at all because the quantum state NF has the unit. Okay, it's only the index of the electron orbit, right? And Ni is only electron orbits, so it has no unit. Okay, so that's the thing we know previously regarding the unit. Okay, so you don't have to get confused with that. This expression is quite simple. It involves not so many things. Okay, it doesn't involve so many things, only the constant and the wavelength. All right. What else? We arrive at this example and we're gonna solve it, right? At the state n equal to 2, okay, the leadback constant พวิทย์นะพวิทย์ชื่ออะไรวะ เพิ่งเข้ามาครับ okay, the leadback constant could be applied to any orbits in the hydrogen atom. Okay, you know hydrogen atom ใช่ครับ okay, yes, the hydrogen atom is the basic, the fundamental atomic structure because it has only a single electron and single proton, so that it would serve as a basic atomic structure to us. All right, as I said, n equal to 2 of the hydrogen atom, find the kinetic energy, potential energy, and the total energy of this atom. Okay, and that's the first sub question. What about the second sub question? They want to know the wavelength of the proton or the photon, and from the electron transition to state number n equal to number 1. Okay, so let's start with this problem. We will n equal to 2, right? Hydrogen atom. Okay, let's talk about this initial state here, n I equal to 2. At the second stage, we would deliver the answer, right? The answer to potential atom, which is potential energy, which is the Coulomb energy, actually, right? E equal to KQQ by n, right? So UN is actually this value, right, which is 2 times En, right? And what else? The Kn is the negative value of the En, right? And of course, En is 30.6 divided by n squared, right? We know that En is negative 30.6 divided by n squared. That's the approximation only. All right. So now, oh, I'm sorry for that. I forgot to turn off the lamp. ลืมปิดไฟข้างบนให้นะครับก็ลืมเปิดคือเมื่อเช้านี้ผมยุ่งกับเขามีอะไรงานทำบุญใส่บาตรอะไรอย่างเงี้ยครับก็เลยวิ่งเอาของไปฝากครับลืมเซตอะไรหลายอย่าง this one close. Yes, 13.6 divided by n squared. That's the amount of total energy at this at that atomic orbit. Okay, this is the route where electron could move around. Okay, and please note that the total energy is negative because it's the combination of potential energy and the kinetic energy. Because potential energy is twice in magnitude of the kinetic energy, so the total is going to be negative because this is negative twice, right, and positive one, so the summation is going to remain something negative, right? Anyway, we will we'll try to find first the E2, right? Because we are talking, we consider the energy level as in equal number 2. So E2 will be minus 13.6 divided by 2 square, okay, which is number 4. And once you put it into the calculator, you get minus 3.4, right? 3.4, and the unit for this is electron volts, right? It's, yeah, there you have the answer. In for the potential energy, which is UN, right? U2 is equal to 2 times E2, right? Once you have E2 as negative 3.4, you would get negative 6.8 EV. All right, and that's the potential energy for the second orbit in this example, right? U2 is negative 6.8. You can see here, okay, negative 6.8 EV. And let's talk about the kinetic energy. Kinetic energy is K2, and that's the negative of E2, right? So we have 3.4. We have 3.4 EV. All right. We have 3.4 EV, which is the negative of negative version of minus 3.4 is positive 3.4 EV. So we have the total kinetic energy at 3.4 electron volt. Okay, and that's it for the whole thing here, right? Yeah. I hope that everyone could understand it, right? It's not too difficult. Let's talk about the wavelength of the photon emitted from the electron transition to state n equal to 1. N equal to 1. So let's say we have here n equal to what is that? This n equal to 2, right? That's the initial state, and the final state is NF, which is number 1. All right, the electron is this one, and is moved to this state, and once the electron reduce its orbit to the lower one, right? There will be energy releases from the orbit transition, and this one is called photon. And photon is a kind of light. It has C equals to lambda F, right? There will be frequency of the light, there will be wavelength of the light, but the product of this is gonna yield the light speed, okay? It cannot be greater than this, the velocity of anything. Okay, we want to find the wavelength, right? Find the wavelength of the photon. So we need to consult the Leadback expression, which is this one, 1 by lambda equal RH 1 by N F square minus 1 by Ni square. Okay. One by Ni square. And yeah, we go ahead with the determination here. But of course, you once you convert it, lambda from state number 2 to state number 1 is going to be 1 by RH, and there you have Ni square minus Nf square, and you have here in F square Ni square divided by Ni square minus Nf square. All right. And yes, 1 by RH. RH is the Leadback constant. And where is that? Leadback constant is provided here, which is 1.09. 1 by 1.09. 377 times 10 to 7. And Nf is the final state of the electron orbit, right? Final state is the number 1. So we have 1 square, and initial state is number 2 square, divided by 1 Ni. Ni is, where is that? Is number 2, right? So 2 square minus 1 square. So you would have here RH in 4 by 3, right? And 1 by 1.09. 737 times 10 to 7. And there you have the results. And we could use the calculator, right? ทุกคนตอนสอบนี่มีปัญหาเกี่ยวกับเรื่องเครื่องคิดเลขเอาเข้าได้ไหมครับผมพยายามระบุให้คุณไปแล้วนะว่านำเครื่องคิดเลขเข้าได้นะครับ is 3 by 4 by 3, right? Four by 3 times 1 by RH, right? It's equal to the wavelength, right? It's 1.215 times 10 to negative 7 and nanometer. Oh, no, meter. I'm sorry for that. It's in SI scale, right? Meter. And once you convert this to the appropriate scale, like in nanometer, right? Because most visible lights could be expressed in nanometer. So you just multiply this one by 100, and this one is going to reduce it by the order of 2, right? So it's 10 to the negative 9, and that's the nanometer. So once you multiply this one by 100, the first number is going to be 121.5. Okay, and here is nanometer. Okay, and that's it for the nanometer for the photon right here. Is that all right? One 21.553136. Okay, nanometer, and that's correct. Okay, and that's the story about the first example in Leadback formula. Okay, but if you take a look at the whole story here, this is the energy level diagram of the basic atom, right? The hydrogen atom, which has only a single proton, single electron. There is no neutron at all. And yes, we have several orbits for electron to move around. The first level here is number one, right? Energy level number one, and the energy is pointing upward like this. And you will see, you may ask me why the number here is larger, right? But it's larger in magnitude. Okay, it is in the infinity, which is very, very far, extremely far from the nucleus. You would have zero energy for electron to move around, right? And for the first state or the first orbit of the electron, it's going to be -13. This is small, okay? Even 13 is large, but it's negative value, so this one is small. And this one is -3, so it's not big, okay? It's going to be larger and larger, and the highest amount is going to be 0. It has no energy at all. What is energy? It's total energy. Total energy is the combination of the potential energy and the kinetic energy, right? Because the kinetic energy is positive, potential energy is negative, but potential energy is greater in twice greater in magnitude than the kinetic energy. So the total energy is going to remain as the negative value like this. Okay, let's talk about this. Not only Leadback, okay, Bohr has developed the orbits of the electron, and many people try to make a measurement to see whether the Bohr's atomic model is really correct. Okay, Leadback has developed the formula here that we have just used in the previous example in Lyman's. Okay, Lyman is the physicist too. He observed the light that emits the related to the quantum number one, or the first electron orbit. Okay, and that's the first stage. Okay, whether the electron starts from our second state or the second orbit to the first orbit, whether from the third orbit to the first orbit, okay, fourth orbit to the first orbit, fifth orbit to the first orbit. Okay, wherever you start, okay, in this electron orbits, once you arrive at the number one, it's called Lyman series. Okay, because Lyman pay attention to only the light that has the spectrum in related to in relation to the first electron orbit. Okay, and for the second orbit, another person has involved with this task, and that person is called Balmer. Okay, Balmer. ขออภัยด้วยนะครับบางทีผมอาจจะเรียกชื่อติดสำเนียงภาษาเยอรมันนะครับก็คือ Leadback นะ Leadback จริงๆถ้าภาษาอังกฤษจะเรียกว่า Leadberg ใช่ไหมคุณเรียก Leadberg ไปแล้วกันนะผมอาจจะเรียก Leadback มันเป็นสำเนียงการออกเสียงแบบภาษาเยอรมันนะครับใช่ไหม ER มันจะออกเป็นสระแอนะครับแต่จริงๆคุณจะเรียกกันว่าสระเนาะโอเคต้องขอประทานอภัยด้วย Leadberg ก็ได้นะโอเคไหมครับอย่างคำว่า Balmer นะครับก็จะออกว่า Balmer ในภาษาเยอรมันนะครับผมจะออกเสียงติดไปอย่างนั้นนะครับโอเค Balmer series is the series related to the second electron orbit. Okay, when n equal to number 2, wherever you start from, okay, but not the state under the number 2. Okay, you could not start from state number 1 to number 2. You could do that, but in the reverse way like this, it means the electron should get the energy like you project the light to the skin of the metal. In that case, the electron is going to absorb the energy from the light, and it could move from state number 1 to number 2 or to the higher level, okay, because it has now more energy. But for any energy, if the electron starts from state number 2 to state number 1, it will release the energy. Okay, if you start from any higher state number to lower state number, you're gonna get the photon or the light from that. All right. For example, you start from state number 3 to number 2, you get this spectrum. Let's say it's the red light. Okay, the brown one here is beyond the human eyes scope. We cannot observe by human eyes. The brown one here too, the Photon series and the Lyman series could not be observed by human eyes. Okay, only Balmer series could be seen or could be differentiated as the red light, the green light, the blue light, the black one, the blue one, the darker blue one. Okay, this is the visible region for human eyes. That's called Balmer series. Okay, in Photon series is another series that is observed by Photon. Photon is the name of a physicist. Okay, and yeah, if you take a look, bigger view, this is taken from book number 1. It's not big enough. If you look at the figure given by book number 2, you would have Lyman series, you have Balmer series, you have Photon series. Beyond Photon series, as in book number 1, we still have bracket series, which is something about n equal to 4, okay, the 4th electron orbit in the hydrogen atom, and Photon, okay, Photon series is the series related to n equal to 5, okay, n equal to 5 is around minus 0.54, okay, you could say this. It tends to be 0, okay? It tries to reach 0 EV, okay? Do you know EV, right? EV is electron volt, is a tiny scale of energy for the electron to live in that orbit. All right. Both spectral series of the hydrogen atom is somehow like this. Several series are observed by different physicists. Okay, if you want to have your name in this table, you need to pay attention to the spatial series, and the people will accept your idea, and they are going to use your surname as the name of the light, okay, emitted from any atom. Okay, you go further. If there is a gap, just do it, okay, and publish your work, and the people will use your surname. Will say, I will call your surname as the series of the lights, okay? But you should have your own laboratory. You should have also measurement device, okay? Okay, the first 2 figures are shown in the linear scale, okay, linear way. The line here is straight line, and if you see it in a circular way like this, you could see it in a circular way, okay? It's suitable to the realistic situation because the shape of the atom is sphere, right? It's spherical. So if we look at in a cross-sectional view in a 2-dimensional plane like this, the spherical shape is going to be seen as a circle like this, right? Okay, Lyman starts from wherever to n equal to 1. Okay, the first electron orbit. Balmer series starts from wherever orbits, whatever orbits, and you reach n equal to 2. And that's the visible light, as I told you here. Lyman series belongs to the ultraviolet region, and Photon series is the case where you start from whatever electron orbit to the 3rd electron orbit. All right, and yeah, it belongs to infrared region. It cannot be detected by our human eyes. You need to have special device, infrared camera, infrared sensor, or something like that, infrared film or something like that, or infrared scope. Okay, and bracket theory is the light related to n equal to 4. Okay, you start from wherever electron orbit, whatever electron orbit, and you reach n equal to 4. For the full series, you start from whatever quantum states, electron orbits to n equal to 5. Okay, I don't know when n equal to 5. I don't know the name of the series. Maybe it's your name if you want to observe it. All right. Yeah, the first 5 series are the most considerable one in physics, right? So let's pay attention to the one that could be observed by human eyes. That's the Balmer theory. The Balmer theory has something to do with n equal to 2. Okay, the second electron orbit. Okay, when the quantum number is n equal to 2. Okay, please note that n is the principal quantum number. You will see 3 quantum numbers more. Okay. And today you are gonna see the spin, okay, which is a kind of quantum number, okay. And as in figure 21 and figure 23, 21, okay, in straight line, 22, and in figure 23, it's in the circular way, okay. Okay, our example here is taken from book number 1. They consider the Balmer series. Find the longest wavelength of the emitted photon and its frequency and energy. Or they ask us 3 quantities: the wavelength, the frequency, and the energy. All right. For the second sub question, they ask us about the shortest wavelength of the emitted photon only. There is no need to find the frequency and energy for this one at all. Okay. Let's do it. We open the new page, right? So, but one thing we need to keep in mind is, what is the longest wavelength? What is the longest wavelength? Okay, if you take a look at the diagram of Balmer series is the case you start from whatever quantum state or whatever electron orbit, but you have to reach the second orbit, right? Like here, right? The length of this arrow, of this vector, is the amount of the energy it's going to be released by the electron transition to photon, right? The packet of energy. So what is the longest arrow that could take place in Balmer series? You could see that this vector, which starts from n equal to infinity, this is going to be called maximum energy, right? Maximum energy. And this vector, the vector from 3 to 2, that's the minimum energy. Okay, the minimum energy. Because this one has the shortest length, okay, in terms of energy, the lowest amount of energy transition, that's the minimum energy. Here is the maximum energy. You start from an infinity, which is very, very extremely far away from the nucleus of the hydrogen atom, and you reach the second electron orbit, and that's the maximum energy that is possible to the Balmer series, right? The minimum energy will give you the longest wavelength, right? What is the reason behind? Because if you take a look at the Planck-Einstein relation, E equal to HF, and as you know that C is equal to lambda F, right? Or you could say F is Z by lambda, right? And if you put F equal to C by lambda into this expression, you're gonna get H Z by lambda, right? H Z by lambda, and after that you would get the energy. All right. You will get the minimum amount of energy once you have the greatest amount of denominator, which is the longest wavelength, right? E min will happen once you have maximum value of the wavelength, okay? So E min will correspond to lambda max, okay, the maximum value of lambda max, and E energy will be maximum when your denominator is minimum. Okay, if this one is very, very tiny, the denominator is not large, the whole thing here is going to be bigger, right? So E max, the maximum of energy, will take place when you have the shortest wavelength, which is the minimum. Okay, is that understandable to you? You have to make the analysis by yourself. Okay, E is equal to HC by lambda. If the denominator is large, you get the minimum amount of energy. If the denominator is minimum, you get the greatest amount of energy. All right. So let's get back to the question. They would like to know the longest wavelength. So the longest wavelength is this one, the maximum value of lambda, right? And they want to find the frequency. So frequency is going to be this expression, right? F min equal to C by lambda max, right? The minimum frequency that could be possible. And Emax too, right? Yeah, let's go further. Lambda max, lambda min, right? So where is that? Okay, let's find first what is the longest wavelength, lambda max. What is that, right? So in order to find lambda max, how lambda max take place? Lambda max will happen once you let the electron start from n equal to 3, the third electron orbit, to the second electron orbit. So Ni is number 3 to Nf, the final state is number 2, right? So lambda max will take place from this one. So let's get back to the Leadback formula. Leadback formula says that this one, right? 1 by lambda is Leadback constant times 1 by Nf square minus Ni square. And we end up with the result, the closest form is something like this, right? Lambda initial state to the final state 1 by Leadback constant in F square in I square in I minus in F square. So we're going to use that lambda max will be the lambda that starts from state number 3 to state number 2, right? Third electron orbit to the second electron orbit. And from this expression is going to be the reverse, the reciprocal of the Leadback constant, and NF NI square divided by NI square minus NF square. All right. And as you know, NF, the final quantum state, the quantum number is number 2, and initial is number 3, NI is 3, and F is 2. So the Leadback constant is where is that? Leadback constant H, right? 1.097 approximately 10 to 7. Okay, 1 by meter, that's the unit for the Leadback constant. And we have NF as the number 2 times N initial, number 3 square divided by NI square. Initial is 3 square minus 2 square. The final state is number 2. So you get 36 above, right? 36 divided by 9 minus 4, which is number 5, okay? And 1 by 1.097 times 10 to 7. Okay, and let's make the computation by putting everything into the calculator. You get 36 by 5, right? And yeah, by RH, you have to multiply it by the Leadback constant. You get 6.5611 times 10 to negative 7, and the unit is meter. All right, you get something like that, and lambda max is somehow that. But the meter is not appropriate unit, right? Because we have to deal with Balmer series is the series of the light that could be observed by eye, and typically the wavelength would be represented in nanometer, right? If you take a look in the visible light, the wavelength is usually said in nanometers. So we will talk about we have to convert this amount into nanometer scale. So it's equal to, you have to multiply this one by 100, right? And this one is going to reduce to 10 to negative 9, and that's the nanometer. So 656.11 nanometer, okay? And that's the greatest wavelength you could get from the Balmer series. And let's talk about the next thing. They want to know no, not this example. And the next one. Okay, they want to know the frequency, right? Frequency, yes, of course. You know that F is C by lambda. F is C by lambda. C is the 3 by lambda is lambda max, right? When the wavelength is maximum, the frequency is going to be the minimum, right? The frequency is going to be the minimum, and that's you could get the smallest value of the frequency from the Balmer series. Okay, once you put 3 times 10 to 8, okay, for simplicity, actually it's 2.99 blah blah blah. We don't need to be so precise like that. Lambda max is 6 because we are in the primary in the high school level. So 656 times 11 times 10 to negative 9, right? And you put it into the calculator. Okay, that's the lambda max, right? Lambda max, somehow that. And once you F min C, which is okay, C is 3E8, right? F min is C by lambda max. It's going to be 4.572. 4.572 4 times 10 to 14, and the unit for that is hertz. Okay, that's the unit for this is the minimum value of the frequency that you could get from the Balmer series for the light. Okay, and the next quantity they want to know is the energy here. Okay, the energy. So now we get to the Bohr formula again. Okay, energy from 3, okay, state number 3 to state number 2, okay, the third electron orbit to the second electron orbit, 3 to 2, and it's going to be equal to E initial to E initial to E final, right? E initial, which is E2 minus E3, okay? And yes, of course, you know that E2 is negative 13.6 by 2 square, okay? And minus 13.6 by 3 square. All right, you put it into the calculator, right? And moment, you could bring the same thing together, right? It's minus 13.6 in 1 by 2 square minus 1 by 3 square, and if you put the negative sign inside the parentheses, you get 13.6 in 1 by 3. All right, yeah, 1 by 3 square minus 1 by 2 square. Okay, that's the stuff for us in this E322. So you would get 13.6 and 4, is that correct? Initial, no, initial is 3. I'm stupid, because we start from 3 to number 2, right? So 3 to 2. So this one is going to be 3 3 and 2, and once we move the negative sign into the parentheses, we get 2 square and 3 square. So we have at the first position number 9, and the second position is number 4. In 4 and 9 is going to be 36, right? So 13.6. Let's put them into the calculator. 13.6 times 5 by 36. It's 1.999 and 8889. 1.8889. Energy of this is in EV, right? And let's check whether the minimum is the minimum, right? Minimum energy, this corresponds to the minimum energy, E min. Okay, minimum energy is 1.889. All right, 889, minimum energy. Where is that? If min E min is here, okay, you could see that minimum energy correspond to 1.8889. All right, IEV. Okay, and that's the whole thing for this story, right? But no, not yet. We still have one remaining quantity to find, right? Which is the shortest wavelength of the emitted photon. The shortest wavelength is the result from the maximum energy right here, because if you take a look at F equal to C by lambda, F equal to C by lambda, if you want to find the shortest wavelength, right? Shortest wavelength, hold on. E HC by lambda, okay, E HC by lambda. E is HC by lambda, okay, and the lambda, once the lambda is shortest, you get the maximum energy, okay. So the shortest wavelength could be found from the Leadback formula again, okay. The Leadback formula is 1 by lambda is 1, oh no, it's equal to Leadback constant. Leadback constant in 1 by n I square, right? I think if I can remember properly, n f square minus 1 by n I square. Okay. So the shortest wavelength is due to the maximum, correspond to the maximum energy, right? It means you start from n equal to infinity to n equal to number 2. So lambda from infinity to number 2 could be found from what is that? Once we have already is 1 by Leadback constant, right? And in f n I square divided by n I square minus n f square, right? Okay, that's the explicit form of the Leadback constant for the wavelength, right? And once you know that the wavelength, oh no, we should not use this expression, otherwise it's going to be difficult. Okay, let's forget about this. Let's forget about this because it works, but it's difficult for you to understand. Okay, let's use this expression. You know that in initial is infinity. This is the incorrect mathematics. Actually, you should say ni tends to infinity because infinity is unreachable. Nf is number 2, right? So once you put an infinity to this location, infinity square, right? It's going to be a very large number, and 1 by infinity square is going to remain 1 by n square will remain 0, right? Because it's a large number. So lambda min finally will be in f square by RH, okay, the Leadback constant. The Leadback constant Okay, lambda min, which is the minimum wavelength, right? Which is actually the wavelength from infinity to the second electron orbit, could be found from NF, which is the number 2 square, right, divided by 1 point. What is the Leadback constant? Where is the Leadback constant? Okay, 1.0974 times 10 to 7, right? You will get the minimum wavelength from these 4 by Leadback constant. That's the lambda min. Okay, and it's equal to 3.6451 times 10 to negative 7, and it's in meter. All right, 3.6451 e to negative 7, and it's in that's the inappropriate unit, right? We're gonna express it in nanometer, right? We have to multiply the left number here by 100, and this one is gonna reduce it to 10 to negative 9, and that's already nanometer, right? So it's 364.51 and nanometer. Okay, so that's the minimum wavelength we could get from the Bauer series. If you are not sure whether it's the minimum wavelength, you could compare it to the maximum wavelength. The maximum wavelength we could find from the Bauer series is 656. Okay, 656, and this one is only 364. Okay, which is smaller than the maximum wavelength we could obtain with before. Okay, now we move further to the next story in this lecture, and that's the topic about the radius of the atom. Okay, the radius of the atom could be found hardly. Okay, it's quite hard to find the radius of the atom, but we can approximate somehow, and the radius of the atom depends directly to the quantum state, which is the electron orbit. Okay, if the electron orbit is far away from the nucleus, the radius of the atom is going to be big, right? If the electron orbit is so close to the nucleus, we have a small size of the atom, right? So the radius of the atom depends on the electron orbit. So radius n, okay, I should have the subscript as n, okay, because n is the integer corresponding to the quantum state or the electron orbit. Okay, that's the principal quantum number, right? And the physicists have already derived the expression for the atomic radius like this. Okay, n square and h slash square. Okay, you know earlier that h slash square is the reduced Planck constant. Or if you want to express it in the full Planck constant, you get something like this. And once you substitute every term, epsilon 0, mass of electron charge, the Coulomb constant, the electron permittivity, the electric permittivity, you would get 0.05293 in square nanometer. Okay, this is the unit already, the scale to nanometer, which is the same scale as the wavelength of the visible light, right? So we need to introduce another mass unit, which is called atomic mass unit. This might be well known to you in chemistry, right? Atomic mass unit is known to you, okay? It's number 1, number 2, 3, like is an integer. But in physics, yeah, it's the same thing. It's defined from 1/12 or 1/12 of the mass of the carbon 12 atom. Okay, you know from chemistry that for a certain element, there could be many isotopes, right? It's like a brother or sister of that for you, okay? It's like your brother and your sister belongs to the same family, but it has different number of neutrons, and the different number of neutrons is gonna bring you to another isotope. And carbon too. Carbon could have the atomic number like 13, 14. It's called carbon 13, carbon 14. But the fundamental carbon is carbon 12. Okay, once the number of proton and electron, so the number of proton and neutron elements 12. Okay, so we have carbon 12, and if you divide the mass of carbon 12 by 12, it's going to be called the unit of atomic mass, or simply speaking, atomic mass unit. Okay, this is what you may have ever heard in chemistry before. Okay, let's go to the table that summarizes everything about several components in the atom. Okay, we have 3 fundamental subatomic particles. The first one is neutron, the second one is proton, right? You know, okay, let's draw. You have proton, you have neutron staying at the nucleus for any atom, right? And you have electron moving around, right? And for hydrogen, we don't have neutron at all. We have only a single proton. And let's get into the detail of several characteristics of these 3 subatomic particles. The symbol, okay, the symbol of neutron is N with a power of 0. When the power position here signifies the charge of that particle, because neutron has no charge at all, it's 0. So N with the power of 0, okay, raises to 0. And if you want to write it in atomic expression, it's going to be N, right? Small n. The number of proton and neutron here is, okay, the total number of proton and neutron in the nucleus is 0. No, the number of proton here is 0, and the number of neutron is the number of element in the nucleus is number 1, because there is only single neutron. Okay, it's neutron 1, 0. For the proton is a kind of positive charge, right? It has positive charge, so we say P with power plus psi. And in atomic expression, proton has 1 proton. Proton has 1 element in the nucleus with the number of neutron and number of proton. We have single proton right there. Okay, and for electron has a negative charge. We use E later to represent electron, and we write down the power, the superscript here, the negative side, because we want to represent the negative charge of the electron. And in terms of atomic expression, we have E0 minus 1, because in the nucleus, we don't have we don't have either neutron or proton. Okay, we have neither proton nor neutron, and in the nucleus, because this is only the electron particle. And let's talk about the the lower one, which is -1. Okay, the number of proton, of course, it is not proton, it's electron, but we still write the number of proton as the missing one, which is -1. Okay, in the reverse way. Okay, you could see that here we, for the single proton, we write down the number 1 at the left subscript because there is a single proton. But for this expression, there is no proton, it's electron. Electron is the opposite particle to proton, so we write down here -1. Okay, and the number of particles at the nucleus is 0 because there is no neither a proton nor neutron, so it's 0 here. So let's talk about the location. The neutron stay at the nucleus. The proton stay at the nucleus too, and the electron stay at the orbit. Okay, because it's moved around the nucleus. It doesn't locate at the nucleus or the center of the atom. Okay, and let's talk about the mass of these 3 subatomic particles. Actually, this is these are not the basic particles. If you go further in bachelor degree, master degree, or doctoral degree, you will see the fundamental elementary particles, right? You will see it later. The mass of these 3 particles could be expressed in different way. Okay, it depends on which situation you're gonna use it. For example, in the typical way, we use the SI scale, right? In terms of kilogram, the neutron has the mass of 1.67 times 10 to negative 27 kilogram. Okay, it's very, very tiny. You cannot pick up only 1 neutron simply, okay, because neutrons stay with so many other particles or even with themselves. Proton has the mass of 1.67. You could observe that 1.67 are the same amount, right? But if you go further after the second position in the decimal unit, this is number 4, this is number 2. Okay, neutron is a little bit heavier than proton, but it's in the same scale, 10 to the negative 27 kilogram. For electron is even tinier and has less mass than neutron and proton. The mass of electron is only 9.1, 10 to -4 and -27. That's -31. So the mass of electron is 9.1 times 10 to negative 31 kilogram. Okay, and that's very, very, very tiny. And in another sense, if you want to compare the mass of any particle with respect to the mass of electron, it's going to be, for neutron, 1,842. For proton, it's going to be 1,836. You could see that neutron is a little bit heavier than the proton, 42 and 36, right? So proton mass is a little bit greater than proton. And for electron, since we have the relative mass here, mass of electron divided mass of electron is going to be 1, simply number 1. For the people working in chemistry, the atomic mass unit, right? That's quite important to you. The atomic mass unit, which is here, right? The 1/12 of the carbon-12 atom. And if you want to see the atomic mass unit in SI scale here, that's the case. 1 atomic mass unit is equal to 1.66 10 to negative 27 kilogram. Okay, which is very, very tiny. And if you want to express it in the atomic mass unit, neutron has the mass of 1.0086. Okay, for proton is 1.0072. So neutron is heavier than proton. Okay, and that's the atomic mass unit. It's not perfectly number one. Okay, but for the people in chemistry, they may simply use number one, but for us in physics, it's not. We need to use something more precise. Okay, for electron is even lighter than neutron and proton. It has less mass, and once we convert it or compare to the 1/12 of carbon 12, we're gonna have 0.3 times of 0 and 5/4 blah blah blah. Okay, and that's much less than 1 atomic mass unit for electron. Okay, and for the people working in relativity theorem, there is an expression which is called E_mc², right? E equal to mc², and that's the Albert Einstein expression. And the people have adopted his formula to build up the nuclear bomb, right? Which is not, which harmful to everyone, right? Okay, in terms of relativity expression, EMC², the mass, EMC² means mega electron volt by c². Okay, the mass of neutron is 939.57 mega electron volt by c². You know that electron volt is the unit of the energy, right? And mega is 10 to 6, right? 1 million electron volt by c². C² is the speed of the light, okay, with the power of 2. So neutron has the mass of 939. Proton has the mass of 938. So of course, 38 is less than 39. Neutron is heavier than proton. Again, here you could see that. And for electron, the mass in special relativity theorem, electron has the mass of 0.511 only. Okay, it's less than 900. You could see that the mass of neutron and proton is around 1,000 heavier than each other, or 2,000 here, 1,800. Okay, approximately. And in order to calculate the chart, you have to look at the elementary figure of the proton and neutron. Okay, here, this is a standard model of elementary particles. Okay, and yeah, I'm not sure whether you could see it, but I just put it for you to inspire you if you want to work in physics in the future, right? If you want to become a physicist, okay, this is a good idea. And they're going to use your name, your surname in some situations. Okay, proton here. Okay, proton is not the smallest particle. Okay, that's what I learned during my generation. But in your generation, the current situation is that proton could be divided into some tinier particle, and that is called up quark. Okay, W. The letter U represent up quark. The letter U here represent also another up quark. It's an elementary particle. I will talk about our particle later soon. Okay. Proton has 2 up quarks and 1 down quark. All right. And neutron has 1 up quark, 2 down quarks. Okay. A little bit different, right? But both are the same thing. Okay. Both are the particle staying in the nucleus of of any atom. Okay, except for hydrogen. Hydrogen doesn't have proton, neutron at all, right? So proton is composed of 2 up quarks. Okay, and that 1 down quark. For the neutron, we have 2 down quarks and 1 or single up quark. And in order to compute the charge, and one up quark has the charge of minus 1/3, and one down quark has the charge of 2/3. Okay, so in order to compute the charge of the proton, one up quark has the charge of 2/3, and one down quark has the charge of minus 1/3. Okay, up means positive, down means negative. Once you have two up quarks, you have to multiply by 2, right? And a single up quark has the charge of 2/3. So proton is composed of 2 up quarks, so you have 2 times 2/3. And for the single remaining down quark, one down quark corresponds to minus 1/3. So you have minus 1/3 here. And this one is 4/3. 4/3 minus 1/3 is going to be number 1. Okay, so that's why proton has a charge of 1. Okay, positive 1. And let's talk about neutron. Neutron has a single up quark, which correspond to 2/3 charge. Okay, and neutron has 2 down quarks. 2 down quarks here, right? The red one and the green one. And one down quark has negative 1/3 charge. Once you have 2 elements of the down quark, you have to multiply minus 1/3 by 2. And once you make the calculation, the simple calculation, 2/3 and negative 2/3, it's going to remain 0. So that's why neutron doesn't have charge at all. All right. For the electron has a charge of -1. Okay. And spin. Okay, spin is another property or characteristic of these 3 subatomic particles. All of these particles have the spin number as 1/2, 1/2, 1/2. Okay, and in order to better understand the behavior of this proton neutron, let's take a look at the standard model of elementary particles. Okay, elementary particles in physics. This is beyond the scope of your high school level. Okay, this is the story in bachelor degree or even in doctoral degree level. Okay, yes, here is the quark. Okay. Here, okay, let's classify it. This is the elementary fermions. Okay, fermions is, and here is called the violet one is called quarks. Okay, quarks also here. And leptons is another type of elementary particle, which is which are denoted by the green one. Okay, and that's the fermion. Okay, and for the last second columns here, it's called bosons. Okay, boson. Boson comes from the surname Bose. Okay, Bose is the surname of a physicist, and is also again fermion comes from the surname of physics. Okay, the quarks, once you know we have up quark and down quark. Okay, one up quark, let's zoom it. Okay, the one up quarks will have the charge of 2/3, and one down quark has the charge of minus 1/3. And once you make the summation for the neutron, Neutron has 2 down quark and 1 up quark, right? This is up, okay, down, and quark is here. You know that in this, on this page, neutron has 2 down quark, which is this one, down quark, and a single up quark, which is this one, okay? But neutron pick up 2 down quark to compose themselves, right? To construct themselves itself. And let's take a look at the chart. The chart by for neutron will be 1 up quark, which is 2 by 3 here, okay? 2 by 3 for the single up quark, and 2 down quarks, 2 times of negative 1 by 3 here. And once you make the calculation, that's why you get 0. Neutron has no charge from this reason. And proton is in a similar way, right? Proton is composed of 2 up quarks and a single down quark. So let's take a look at the chart of the proton. Proton has 2 up quark, so 2 by 3 2 times, and that's why we have here 2 times 2 by 3, and a single down quark, so we have 1 times minus 1 by 3. We have 1 times 1 by 3, and once you make a summation, 4 by 3 minus 1 by 3 is going to remain number 1, and that's why proton has a single or 1 positive charge here. Okay, and let's take a look at the electron values. Electron, anybody could observe electron in this table right here. Okay, electron is here. Electron has the charge of -1. Okay, -1, and you could see that the spin number, okay, spin number for the up quark is 1 by 2. Spin number for the down quark is 1 by 2 too. And for proton and neutron, it's composed of, whether it's composed of 2 up quarks, 1 down quark, or 2 down quarks, 1 up quark, the spin number is the same, okay, 1 by 2. And that's why we have 1 by 2 spin number for neutron and proton. And for electron, we have 1 by 2 spin number 2 for electron right here, okay? And from this table, you could see that the mass of electron in terms of mega electron volt per c squared is 0.511. And you could see that 0.511 appears here in this table, right? Mega electron volt per c squared. And what about the down quark, up quark, and so on? You could not say that you make a summation of down quarks and to up quark, you get 938 or 939, because we need to have some more, put more mass into this, so that the energy will be the energy that try to combine all these 3 subparticles to stay together. Okay, you cannot say 2 by 2 times 2 by 2 plus 4.7. No, it's not the case. It's much less than 900. Okay, proton and neutron has much more mass than the summation or the combination of up quark and down quark. Of course, they need to have more mass in order to convert their mass to be energy to attract several subparticles to stay together. Okay, we will talk about that later, and we have also the computation for that. What else? Okay, this one is the elementary particle. Okay, what about photon here? Photon is what we have just seen, right? Photon has no charge. Here you can see there is no charge for photon. Is denoted by the gamma alphabet here, okay? And photon has 0 mass. Okay, if you take a look at these boson. Okay, it's not the case, right? Photon has no mass, photon has no charge, but photon has spin number as number 1. Okay, photon is a kind of elementary, but for atomic, for atom, there are only 3 subatomic particles: neutron, proton, and electron. Photon is the result once electron reduce their position from the upper orbit to the lower orbit, right? To the big quantum number to a lower quantum number. So the electron will emit the photon, and photon has no mass, photon has no charge, but the spin number of the photon is number 1. You will see later what is the spin number. Okay, yeah, and that's the whole thing in this table. Okay, we need to stop so that we would align at the same topic as M604. Okay, the homework today for you, for both M604 and M605, is that you need to find any problem related to the Leadback formula, or you find any problem related to the Planck formula, E equal to HF, right? Okay, find the energy level, find the frequency, wavelength, of the electron transition from one electron orbit to another electron orbit. Okay, and what else? Nothing more, right? So that's seeing a homework, right? So that we can use it as the collective matter. I don't know how to. Yeah. Yes. 5.1 problem with relation to this story. Okay, and yeah, see you on Wednesday or next week. I'm not sure which day I should have the compensation lecture due to the mixing lecture in the last week, right? Due to my duty here at the university, once there was commencement. Okay, so see you on Wednesday. Bye bye ครับ สวัสดีครับ